Hello, thank you for coming. My talk is about reverse engineering custom ASICs by exploiting potential supply chain leaks. Anyway. So, who am I? My name is Thomas. I'm working for Seconsult in Vienna. It's my employer since 2015. And yeah, we have offices around the world and are quite present all over Europe. Short outline, what I'm talking about today. I want to give you an introduction. So what is an ASIC? What are embedded systems which are built around this application-specific integrated circuits? Also the dangers of supply chains, how you can lose some intellectual property, and what are the points which are critical. How to do reverse engineering without having a scanning electron microscope or a focused ion beam station, because I guess most of you don't have access to such devices. Pretty expensive. And yeah, some demo, some live debugging, some printing out of a device which has an application-specific integrated circuit, which is completely undocumented and where you don't get any documentation on the internet or get any clue from the vendor, because it's not labeled with any vendor. And yeah, a small fun fact at the end of the presentation. So what is an ASIC? Who cares and where it is used? So ASICs are basically every chips which are in your mobile phone, which are in your laptop, PC, in your IP camera, and so on. It's just the abbreviation of application-specific integrated circuit, and it can come in every shape. So it can be a system on chip, it can be a single CPU, it can be a dynamic RAM, it can be a NAND memory, and so on. Everywhere where you have logic inside. And yeah, vendors around the world, there are numerous, produce ASICs and use them for different applications. So for radio frequency, for custom instruction sets, and so on. So there are many types of ASICs around the world. And yeah, where it is used. When you just look in your pocket, you have your mobile phone, and there are the ASICs inside. And many of them are commercial off-the-shelf ASICs, so where you get documentation when you just Google the label which is printed on the package. But there are also some chips without any documentation, so where you don't find anything on the internet about it. It gets hard when it's a complete custom solution. So when it's, for example, a system on chip which is produced by some third-party vendor for one vendor who wants to produce a custom system on chip. And yeah, most of the time there is not even a label printed on it. And yeah, the architecture is unknown, the pinout is unknown, everything is unknown. So no, we don't have a datasheet. I was curious about the programmable logic devices, the PLCs, in this case from Siemens, because yeah, they have a lot of them. And yeah, I just removed the housing and looked into these PLCs, because they are computers, basically, like everything. And they have custom system-on-chip solutions inside their PLCs, which are completely unknown. So you don't find a data sheet when you search for both of them. So yeah, that was the challenge. Can I identify some debug port or anything else? So the expensive option would be decapping, looking into the 10, 20, 30 nanometer structures and making pictures and doing reverse engineering of that. So for that you need electron microscopes, focused ion beam stations, and so on, and a lot of time. So no, I don't have a lot of money and a lot of time, so I used the cheap option, just buying a lot of PCPs, which you can find on the internet, which have these the same system on chips, which are on the PLCs, and start to reverse engineer, because you can buy a lot of PLCs, but it's expensive too, $260, something like that. And yeah, so I just hunted for such PCPs on Taobao and AliExpress and so on. Yeah, so that was good news for our CFO, because it was cheap and he was happy. So, what are the dangers of losing intellectual property? When you want to produce PCPs with custom system-on-chip solutions, then you have to give your blueprint to a third-party vendor or whatever manufacturer. And when you are the IP owner, the orange circle on the right, then you want to get millions, thousands of PCPs with the system-on-chip solutions and give it to a manufacturer. This manufacturer says, okay, I can buy all the other parts, capacitors, resistors, and so on from other vendors, from third-party vendors, but the system-on-chip solution has to be created by some specialized chip fabs. So they get the blueprint from this manufacturer. And yeah, you see the two red circles. These two parties have your blueprints. So when something is leaked because of rejects and lands on eBay or some e-waste site or Alibaba, Taobao, whatever, then your intellectual property can get exposed to people like me. And yeah, the other possibility is aftermarket issues. When you are the vendor and have a contract to some customer where you provide devices, and some devices are just old and they get also to the e-waste site or land on some e-commerce website, then it's the same issue, because the PCP gets exposed to hackers and to researchers, and that was in this case the cheap option. Because I was informed before giving this talk that it's not a supply chain leak, but I will say that later. I started with material chasing and landed on Taobao with the same chip, some weird boards. So these PCPs are not part of the usual PLCs. And they were from Shenzhen. You maybe know the city, and flew around the world because my colleagues from Singapore just forwarded it to me. And it was a weird story, but it had a long travel, and then it landed in the hardware lab in Vienna. And you see the boards had different quality, so some of them were a little bit better than others, but one of them worked actually. And that's the same for the second type of system on chip, which I investigated during my research, was the newer one. And I found them on the same site, the same seller, but I got a better price. You see, just 11 euro. And they look the same, so the same good or bad quality, whatever. But it was not the PCP I ordered. I got a different one, like Tinder or profile pics on dating websites. But anyway, it was the same chip, so okay. So I started to investigate with the first batch of PCPs I get from the PLC, with the same system on chip, and I started to investigate which parts of the PCP which which system on chips I know. So where can I find a data sheet and what is what? So you can see on the backside is the dynamic RAM, and also in the center is the flash memory. And it looked pretty much the same like the actual PLC, but it was not the same. And you can also spot on the right picture in the center there is a header. Looks suspicious. What can it be? First of all, I took the PCB with the lowest quality and removed all of the parts to get some kind of circuitry, so schematic, like so that I can just draw which pins are connected to the RAM, which pins are connected to the power, which pins are connected to the flash memory, and so on, to start reverse engineering of the pinout of the actual system on chip. And the header you saw before is, yeah, it looked like a JTAG program interface, a program and debug interface. And in the lab in Vienna, we have a custom solution for brute forcing JTAG interfaces, but you can also do it with JTAG Emulator, Arduino, JTAG Enum, and yeah, there are many tools. And yeah, after connecting my device, the device what I have here, you can look at it afterwards. I got this pinout, and I attached a debugger and was curious because nothing worked. So I thought, okay, sometimes there are some activating, deactivating pins. When you pull it high, it is activated. When you pull it low, it's deactivated, or vice versa. And there was some small resistor, which was next to the pins of the debug interface, and I just tried it out, and it worked. So I got access to the debug interface and had all the options which are the same like the options from a developer, and yeah, that was great. But yeah, it was a little bit hard to figure that out. And I also got the chip ID of the system on chip. And when you look on the internet, it does not exist. But anyway, it's a complete custom solution. And I have also a small figure where you can see which part of the chip ID means what. So what is the part number, what is the vendor code, and so on. And the last bit is always 1. So when you get a chip ID which has a 0 as last bit, then it's maybe not right. So yeah, there are also some other interesting things, because when you brute force the JTAG interface, you does not get the reset, the system reset, just the reset of the state machine of JTAG. And yeah, I was thinking about how can I figure that out. So that's really hard, because it can be anything. The best guess is the pin might be bound to VDD with a pull-up resistor, or it might be bound to VDD via a transistor to switch it. And it's not always clear, but on the second board, on the second system on chip, I figured that out. And in that case, it was switched to ground by a transistor. So on the actual device, when you remove a transistor on the backside, it actually works, but you can use the system reset. And yeah, that's really funny. The easy probe is just to short circuit the ground, the suspected reset pin to ground. And when it lights up or is completely dark or just stopping what it is doing, then you can be sure that's reset. But yeah, be careful that you don't kill your device. For reverse engineering pins where you don't know the interface because there is no attached memory or other system on chip, it's a little bit hard because you cannot be sure, is it an input, is it an output, is it an input and output, or what it is doing. So when you imagine on the left side the inner works of the ASICs, or just the actual circuitry, and on the right the pin of the ASIC, you have some kind of protection circuitry in between, and also some kind of when it is output, then just output logic. When it is input, just input logic, and when it is input and output, both. And you can measure the resistance of all these three options. So when you have a pin where you know that it is input or output or in and out, then you can just probe the other pins where you don't know what purpose they have, whether they are, this kind of pins, because you know the resistance. You can just use some simple resistance measurement exactly for that purpose. But yeah, I didn't use that here because it was easier, and I found the most interfaces, and So for decapping the chips, because there is just the label Japan and some number, I used sulfuric acid. It smells not so good, so be careful and don't do it at home. But you get beautiful pictures with a confocal microscope, and you can also read some labels. And in that case, it was designed by Fujitsu. You can spot it here maybe, Fujitsu 2007. And you were also able to spot which of these pins are connected and which not. So when they were connected to some output, then you see some small notch here, and other pins which were not connected are completely clean. And you can also sometimes spot some not connect labels down there. And I was also digging through literature, so which architecture can it be, and what was really used at this time for such programmable logic devices. And there were different options: ARM, Fujitsu RISC, and FQMC. And to be sure, I just removed the flash memory, used the custom solution to read the flash memory, and then I thought, okay, it's Fujitsu RISC, because when I loaded into IDA Pro, set it to Fujitsu RISC, then it looks like some multiple functions. But just one of the pins were not connected of my reader. After fixing that, I saw, okay, it's ARM. And I also got some strings out there which get referenced in IDA, and then I was able to draw some kind of schematic of some kind of diagram. Where is the core? Where are the modules? Which modules are embedded into this firmware? And that was really cool. I also identified that it may be ARM 926 or 946, but I was not really sure because of the instruction set. You cannot say it all the time. For the second batch, I did the same. Also started with removing the flash chip and the system on chip, and it was also ARM, but a different architecture. And I identified that by removing the SPI flash, the small one here. There's also a NAND flash. The SPI flash just contains the bootloader, so it was not so much code, but it was enough to see which architecture, which CPU architecture at least was used. And it was produced by Renesas and not Fujitsu this time. So that's also the newer series of these logic devices. And it had some similarities to Artec 200P and 400. So they were also designed for such logic devices in an industrial environment. And it was also possible to brute force JTAG in that case. So from the PCP, which was not the one that I ordered because I got the wrong one, but it was better because it had some header with JTAG on it. the other one had no header with JTAG, so it was fine. So yeah, and I also identified that it was Cortex R4 revision 1 P3, so was pretty nice. And then I modified some real world device. So yeah, broke 260 euro, but whatever. You have to do it when you want to be successful. And yeah, when you stop the CPU, in that case, a watchdog runs on an internal hardware module, which is embedded in the system on chip. And yeah, when you leave it too long stopped, then it clears the whole firmware from the device. That was not nice, but at least you can program it. But I saw that after attaching to it and reading and writing some values. So yeah, I broke 3 of the devices, but yeah. I have a small demo where I have brought some PLC, one of the boards that I used in the hardware lab in Vienna, and a programmer. And basically it's just the programmer which is connected to the modified device. And yeah, the super fancy hardware is just doing UART USB. That's it. The UART interface of the PLC was, I think it was, you can find it in a paper of a researcher from the WU Amsterdam. So yeah, in the same city. And yeah, I just used it, and I got the memory address, the memory mapped IO address for the UART from a colleague, from Dr. Ali Abazi. He provided the UART address to me because he did a lot of research by removing this bootloader I mentioned before, injecting code and soldering it back and all this stuff. So he pulled off the whole firmware and got the whole memory map. So yeah, he helped me a little bit. Okay, let's hope that it works. So I have written a small assembly program, and this terminal is just a UART USB connection to the PLC. And I hope when I type make program, yeah, then it outputs Hexpo 2019 and carriage return 9 feet auto. And yeah, that's coming out of the PLC. So I don't have to remove the flash memory chip, reprogram it, solder it back. I can just use JTAG on this system on chip where I don't have any documentation. Yeah, and you can also use the live debugger. So I will restart it. JLink. That's just the software environment for this hardware debugger. And by typing connect, and you type it in the right way, you can just attach to this processor. You see Cortex R4, and I have also connected the software, the system reset, and you can just type R0, and then it stops running. So there is no output coming out. Then you can just set it to default, reprogram it, and it works. So yeah. A fun fact was we had some telephone call, some corresponding with Siemens, and they told us, yeah, it's not a supply chain leak, it's just an aftermarket issue. But that was a good information to me, because when it's an aftermarket issue, then it means this device is sold. So this PCP, which I get with the JTAG header, is actually sold. And yeah, then I looked through some shops, websites, whatever, and I saw that, yeah, pretty similar. So S7-1200 Smart. And I figured out that it was mainly sold in India and China, but not in Europe. And that's the reason why I was not aware of that. But you see the similarities. That's just another series with fewer outputs and inputs, but it's basically the same. So you see there is the same header, there is also a battery, there is the system on chip, the interfaces are the same, and so on. So, yeah. So, do you have questions?
So, thank you, Thomas, for your presentation. We have the time for a question, probably. So, is there any from the audience? So, one here.
What is the time frame that you spend on this project?
So actually figuring out the JTAG was a few days, but waiting for the PCPs, searching the PCPs, writing all the stuff together, weeks, months maybe. But no, working on it few days. It's not so complicated. When you have some practice, then it's definitely possible in few days.
Thank you.
Any other question? Like a quick one, probably? Still have 1 minute. No? Okay, there. Yeah.
Were you able to retrieve the firmware from the chip?
As I told you, it was cleared after the watchdog recognized that it was stopped. But when you do it at the first time, then you can read the data out from the dynamic RAM. So yes, I would say 70%. Yeah.
Okay, so thank you once again, and thank you for sharing your knowledge.